Hello everyone, welcome to today's video where we'll discussing the thin pressure vessels. A pressure vessel is a container that is designed to hold the gases or liquid at a pressure that is different from the ambient pressure. In this video we'll be focusing on the properties of the thin pressure vessel, their application and how they are designed. The first question comes is how you're going to classify the thin pressure vessel. A thin pressure vessel is a type of pressure vessel that has a very small ratio of thickness to the diameter of radius. In this case, we have thickness to diameter. This ratio is very small ratio. Is approximately equal to 0.05 or even less than that. That is, we have diameter divided by the thickness will be approximately equal to 20. Approximately we claim here T by D is equal to 1 by 15 to 1 by 20. These pressure vessels are used in the industries such as the oil and the gas, chemical, food processing. The most common types of pressure vessels are the pipes, tank, boilers. Boiler is a very large size, so we have to use here number of the steel plate and we have to construct a joint considering the longitudinal joint and the girth joint. Using this we can make a large length of the shell. Design of the thin pressure vessel is based on the theory of elasticity. The pressure inside the vessels exerts a force on the walls causing them to deform. The deformation can be calculated using the theory of elasticity. The design of the thin pressure vessels take into account the maximum stress that can be sustained by the material without deformation or the rupture. Normally two types of stresses will occur. One is called as the hoop stress, which will be also called as a circumferential stress, and other is a longitudinal stress, that is along the longitudinal axis or the axial stress. And therefore the material used for the thin pressure vessel should have a very high yield point. It entirely depends how much pressure you want to store in the thin pressure vessel. Thin pressure vessels are widely used in the industry like chemical industry, oil and gas industry, pharmaceutical industry. In the chemical industry, the thin pressure vessels are used to store and transport the chemicals at a high pressure. In the oil and the gas industry, the thin pressure vessels are used to store and transport the oil and the gas product. In the case of food processing industry, the thin pressure vessels are used to store and transport the food products such as the dairy product, juices and beer. In pharmaceutical industry, thin pressure vessels are used to store and transport the pharmaceutical product at a high pressure. So our requirement here is a high pressure. For this one, we have to design here what is the thickness required to sustain the given pressure. And for that one, we are going to apply the theory of elasticity. There are numerous advantages of a thin pressure vessels over the thick pressure vessels. First is the weight, second is the cost effective and the energy efficient. The thin pressure vessels are lightweight compared to the thick pressure vessels, making them easier to transport and handle. Thin pressure vessels require less material, making them more cost effective than the thick pressure vessel. And the thin pressure vessels have a lower thermal mass, which means that they require less energy to heat or cool. And therefore, whenever you have to transport the beer or the cold fluid or ice creams in the tin pack, then we have a low thermal mass, and therefore the cooling is required when we have to transport from one city to the second city, and air conditioning load will going to decrease because of the thin pressure vessels. That cost will increase if we are using the thick pressure vessels. So thin pressure vessels are widely used in the various industries due to their advantages of being lightweight, cost effective and the energy efficient. Their design is based on the theory of elasticity, and the material used should have high yield strength to sustain the pressure without deformation or rupture. Now we'll discuss two important concepts in the designing the thin pressure vessel. First is the hoop stress and second is the longitudinal stress in the thin pressure vessels. And we'll also discuss how these stresses are calculated and what implications they have on the design of the pressure vessels. The thin pressure vessels provide an important application of the analysis of the plane stress. So if you consider here any element on the periphery, you will get the element here something like this. And because of a very small thickness, this problem is a case of plane stress problem. So only two stresses will exert. One is along the circumference and one is along the longitudinal axis. that is along the axis of the cylinder. Longitudinal axis we will develop here the longitudinal stress equal to sigma L, and along the circumference will develop here the hoof stress. So as shown in this figure, we have diameter is very large and thickness is very small. So in this case d by t ratio, that is the diameter to thickness ratio, is very greater than 1. This one is representing the axis and this one is representing the circumference. So two load will act here. One is along the axis, that will be called as axial load, and one load will be called, that is called as circumferential load. Along the circumferential direction, we have a circumferential stress is developed or the hoof stress is developed. Which one is acting along the circumference of cylinder and is represented by sigma h. The other stress is developed along the axial load, that will be called as the longitudinal, or the axial stress is represented by sigma L. In the third dimension we have a pressure is acting, but we'll neglect the pressure here because the amount of pressure is very small as compared to the hoof stress and the longitudinal stress. So this time the wall will offer a very little resistance to the bending, and it can be assumed that the internal forces exerted on the given portion of a wall are tangent to the surface of the vessel as shown in the figure. The resultant stress on an element of the wall will thus be contained in a plane tangent to the surface of the vessel. Both these are tangent to the surface of the vessel, hence this is a problem of plane stress. When we do the analysis here, we can show here that the hoof stresses and the longitudinal stresses are proportional to the pressure, as well as the ratio of d by t, which is very greater than 1. And we'll prove the relation for the hoof stress is equal to, in the case of thin cylinder, as P into D divided by 2 times of thickness. Since here d by t is very large, therefore the value of hoof stress is much greater as compared to the pressure, that is equal to the internal pressure P. Similarly, we will prove here that the sigma L will be equal to P multiplied by D, where D is the diameter, divided by 4 times of T. And here also, because the pressure is multiplied by d by t and d by t is very much greater than 1, so the longitudinal stress is also very greater than the pressure P. It means that the magnitude of the hoof stress is larger, as even the longitudinal stress is larger as compared to the pressure P. So when we representing the stress on element taken from the wall, we do not usually include the P since it is relatively small, and therefore the stress element in the case of thin cylindrical pressure vessel is modeled as the plane stress. And the shear stress is also not acting this time, so hoof stress will be same as the maximum value out of longitudinal, so that will going to represent the maximum principal stress or maximum normal stress acting along the x direction. So this will be our x direction and this direction will be our y direction, and sigma L is a stress acting in the y direction will be treated as the minimum value of a normal stress, that equal to sigma 2. Shear stress in this case will be equal to 0. So no shear stress act in the case of thin cylindrical pressure vessel. Only two stresses are acting, that is one is hoof stress and one is a longitudinal stress. Since shear stress equal to 0, both the stresses acting perpendicular to the plane will be treated as a principal stresses, that is a sigma 1 and sigma 2 are the two principal stresses, and naturally here the third value of the principal stress will be taken as equal to 0, that is sigma 3 equal to 0. Now this figure represent here a spherical thin vessel. So we have a spherical vessel here of radius equal to r and the thickness equal to t. Since here we have a spherical thin vessel, so ratio of r divided by t is very high and is approximately d by t is equal to 20. So this ratio will be greater than equal to 10. Now vessel is very thin, therefore we'll find here the thickness of the shown vessel is equal to t, and therefore if we show the distribution of the stress, we'll observe here the distribution of a stress is uniform. Both these value here represent here the stress, and the internal pressure will act on the surface of the wall. So this time we have a hoof stress is produced, and we have the magnitude of the hoof stress in a spherical vessel is uniform and is a constant value because the thickness is very small. And in the case of thick cylinder, we have radius is equal to r, thickness is larger here. So this ratio does not hold in this case because of a larger thickness, and when the cylinder is subjected to a pressure equal to P. Because of a large thickness here, what we observed, the stress developed will be non-uniform in the case of thick cylinder, and the pressure is uniformly distributed over the internal wall, but the stresses produced here is a non-uniform stresses. We are not discussing here the thick type of cylinder, rather we are discussing here the thin vessel, either spherical or either cylindrical, and therefore we will consider here the distribution of a hoof stress, and the normal stress is uniform over the given thickness T, whereas in the case of thick cylinder we have a non-uniform distribution. Now we are going to derive here the equation for the hoof stress and the longitudinal stress in the case of cylindrical vessel, and then we will discuss thin spherical vessel. So consider here a thin cylindrical vessel of inner radius is equal to r, and we have a wall thickness equal to T. We'll set up our axis system. Along the longitudinal axis we'll have x axis, and we'll set up the y axis perpendicular to x axis, that is our plane, and z axis is protruding away from the plane. So length of the vessel will be measured along the longitudinal axis, that is along the x axis. So we are interested here the stresses exerted on the small element of this wall with the sides parallel to the x axis, and another one is perpendicular to x axis. Let here P represents the internal pressure, which one is the gauge pressure. So you have to always consider while designing the gauge pressure, and remember that the gauge pressure is always equal to the absolute pressure minus atmospheric pressure. So in the questions they will give the absolute pressure and the atmospheric pressure, then you have to subtract the atmospheric pressure from the absolute pressure. Whatever the pressure is left, that will be our gauge pressure, and entire design is based on the gauge pressure only. Now first we will develop the equation for the hoof stress, and the hoof stress is that stress that occurs along the circumference. This one is a circumference, and along this direction the stress will occur. That stress will be called as the circumferential stress, or is also called as the hoof stress. Or in other words, this stress is perpendicular to the longitudinal axis, that is the axis of the cylinder. So if we show the element in this case, we will show the element like this, and along the circumferential direction, that is along this direction, we have the hoof stress is produced. So for this hoof stress we are going to develop the equation. This hoof stress is caused by the pressure of a fluid or a gas inside the cylinder, and this pressure is exerted on the wall of the cylinder. Thus the pressure of the fluid or a gas inside the pressure vessel pushing outward on the wall of the vessel. This pressure creates a force that is distributed around the circumference of the vessel, causing the hoof stress. So in order to determine here the value of the hoof stress, we detach a portion of the vessel and its content bounded by xy plane. So this one is our xy plane. So we'll take a section of this thin cylindrical vessel at a distance equal to x. Let we have element length equal to delta x. So this elemental length we are showing here. So this one is same as our elemental length equal to dx, and this section is at a distance equal to x. So this horizontal axis running is our x axis, and we have cut it in a xy plane. So this one is representing our xy plane. It has a length equal to delta x. This area here is representing delta x multiplied by t, and this area here also on the top where we have material present is delta x multiplied by t. So this area we observed here is a resisting area, and this area will represent as dA1 will be same as equal to delta x multiplied by t, whereas the same area you can see on the bottom side also, and this area is also equal to dA1, that will be equal to delta x multiplied by t. So half of the section is missing here, so there is a internal stresses are developed, and these stresses we can show parallel to the z axis. This one is our z axis. So this stresses here is along the circumference. Similarly we have stresses along the circumference. So this will going to develop the hoof stress. Let's say the magnitude of the hoof stress equal to sigma h, and the pressure force is exerted on this rectangular plane. This rectangular plane has a dimension equal to delta x, and we have total height is equal to 2 times of r. This pressure force will push it in the inward direction. So this time we assume that the intensity of the pressure is remain constant, and we have pressure force will act on this green area, that will be equal to P multiplied by the area dA2, and this area dA2 will be equal to width is equal to delta x, and we have total height is equal to 2 times of r. So one force is acting in the negative direction of z, and sigma h multiplied by dA1, and is again sigma h multiplied by dA1 is acting on the positive direction of z axis. So if we do the balance along the z axis, then we can develop here the expression for hoof stress. So we'll take here the sum of forces along the z direction must equal to 0. Here the hoof stress is acting in the positive direction of z, so we have hoof stress is equal to sigma h multiplied by the corresponding area equal to dA1, that is acting on the bottom side, and one equivalent value will acting on top side, that will be equal to 2 times. And the pressure force, assuming that this one is uniform, so pressure is assumed to be uniform. Pressure is uniform only in the case of gas, whereas the pressure will change in the case of liquids. As the depth will change, the pressure will also change. We assume here uniform gas pressure, and this pressure force will exactly pass to the centroid of the given area, but we are interested here the total value of the force is same as P multiplied by dA2, and this value must equal to 0. So we have 2 times of the hoof stress dA1 is same as equal to this small hatch area whose length equal to delta x and the thickness equal to t. So we have delta x multiplied by thickness t minus we have uniform pressure, and that is a gauge pressure, multiplied by dA2, that is the area of this green rectangle whose height will be equal to 2 times of r, and the width is equal to delta x. So we have delta x multiplied by 2 times of radius r, and this sum must equal to 0. So 2 will be get cancel here. Secondly, the delta x is also cancel here. So we have sigma h multiplied by t is same as P into r. So we'll get the expression for the hoof stress sigma h, and this value of hoof stress is same as equal to P multiplied by the internal radius r. Remember, the P must be the gauge pressure, and divided by the thickness, that is the wall thickness equal to t. If we replace the value of r is equal to d by 2, in that case we will get the hoof stress equal to P multiplied by internal diameter d divided by 2 times of t. So we have find out here the value of the hoof stress, which is P into r divided by t, where r is the inner radius, t is the wall thickness, P is the gauge pressure and the internal pressure. If d represents the internal diameter, then the hoof stress is P into d divided by 2t. Now we'll develop the expression for longitudinal stress in the case of thin cylindrical vessel. Again we'll consider here one element at a distance equal to x from the origin, and at this distance here we'll take one section which one is perpendicular to x-axis, and we'll cut it and we'll show the separate FBD for the given section plane. So if you cut this thin cylindrical vessel using a section plane perpendicular to x-axis, you will get a section like this, and this area here will be equal to dA1, which is nothing but the circumference will be equal to 2 pi into radius r, and it has a thickness equal to t. So this one is the wall area that is resisting the material, and on this wall area the longitudinal stress will act because this stress is parallel to the x-axis, and x-axis is our longitudinal axis. So let's represent here the longitudinal stress which is parallel to the x-axis, which one is same as our longitudinal axis. So this wall will offer a resistance, and all these stresses, as we have discussed in the case of thin vessel, is of uniform magnitude. Uniform in the case of thin, but is not a uniform in the case of thick wall. And let's say we have the longitudinal stress is represented by sigma L. And this portion here will be exerting here the pressure. So we assume the pressure intensity is constant over this area. So this green area is basically a circular area, and therefore we'll have the elemental area will be equal to dA2 will be same as equal to pi into r square. If it is uniform pressure, then exactly the centroid will be representing here the centroid of the pressure force, and this pressure force will be same as equal to P multiplied by dA2. So pressure force is acting in the negative direction of x, and the stress, that is longitudinal stress multiplied by area dA1, will act in the positive direction of x. So this time we'll do the sum of all the forces along the longitudinal axis, that is along the x-axis, and we'll make the sum equal to 0. So this value of longitudinal stress multiplied by dA1 will be positive value. So we have sigma L multiplied by dA1, and the pressure force multiplied by dA2 will be negative value. So we have P, which one is the gauge pressure, multiplied by dA2 will be equal to 0. Let's substitute and solve this. We have sigma L, dA1 is nothing but the circumference, which is equal to 2 pi r multiplied by t minus P, and dA2 is a circular area, so that will be equal to pi r square, must equal to 0. So in this case the pi term will be get cancelled, one of the r term will be get cancelled, only one r is left here. Longitudinal stress equal to pressure, which one is the gauge pressure, multiplied by internal radius r divided by 2 times of the wall thickness. So almost this value is the half of the hoop stress, or in terms of the diameter you will get this longitudinal stress equal to pressure multiplied by internal diameter d divided by 4 times the thickness, that is the wall thickness. So this value is also equal to half. So in general here we have longitudinal stress is always equal to the hoop stress divided by 2, or we have the hoop stress is always equal to 2 times of a longitudinal stress. So hoop stress is always larger in the case of thin cylindrical vessel. So design is based on the hoop stress and not on the longitudinal stress. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.